All right, this video is going to go over the key parts of the worksheet that we did that you guys completed. Key things you need to know. First thing, Bronsted-Lowry bases in the it says which are Bronsted-Lowry bases in the following equilibrium. So the first thing you have to look at is, well, remember when we do Bronsted-Lowry acids and bases, whoever gains an H and whoever loses an H. Well, at this point, this has two H's, this has three H's. On the other side, this has four, and that has one. So if you go from 3 to 4, that's going to make that a Bronsted-Lowry base. That's going to go to 2 to 1. That's going to make that a Bronsted-Lowry acid. Going the other way, though, this would be considered, if this is an acid going this direction, that would be a conjugate base going that way. So the correct answer for this one would be B. CH3CO minus and OH minus. So remember, a Bronsted-Lowry base gains an H, Bronsted-Lowry acid loses an H. Definitely have to be able to do that. Number 2, which of the following pairs of species is not a conjugate acid-base pair? The definition of a conjugate acid-base pair means there's only a single H difference. So like for example here, if I have OH2 minus and OH minus 1, or O2 minus and OH minus 1, the only difference is a single H. That's the only difference. So that is a conjugate acid-base pair. If you look at H2CO3 and HCO3 minus, the only difference, this goes from two H's to one, so this would be the acid, that would be the conjugate base. C is the one that is not a conjugate acid-base pair. It's simply because of this. If you look, HNO2, if you remove the H, you end up with NO2 minus. So this is the acid, that would be the conjugate base. So the difference between a conjugate acid and a conjugate base pair is a single H, and make sure the charge reflects that. That's why number 2 is the correct answer. Number 3. Which is a conjugate acid-base pair for the following equilibrium. Okay, so if we look here, we're looking, let's see here, H2O is the acid, OH minus is its conjugate base. At this point, this has 2. You go over here, it has 1. So at this point, it loses, so it's acid. This is a base. This is a base here because it goes from 1 H to 2 H's according to Bronsted-Lowry, so that's a conjugate acid. So when it asks you for a conjugate acid-base pair in this case, remember the difference is going to be a single H. H2O is the acid and OH minus is its conjugate base. Next one. What is a conjugate acid? To get a conjugate acid, you add an H. To get a conjugate base, you take an H. So if I take H2PO4 minus, if I tack an H on there, I'm going to get H3PO4 with no minus charge because the H will cancel it out. The correct answer for that one would be B. Next one, number 5. Which of the following reactions is not product favored? Remember, a product favored reaction means you're going to produce a lot of products and very little reactants. In terms of acid-base, any weak acid or weak base reaction, 95% of the reactants stay together and you only produce roughly, at best, 5% products. So really, when it says it's not product favored, you're looking for the weak acid or the weak base. HCl, strong acid. HCl4, strong acid. NaOH is a strong base. H2SO4 is a strong acid. If you look, ammonia NH3 is a weak acid. So by definition of being weak, only 5% of it at most would produce products. Therefore, it is not a product favored reaction. The K value would be less than 1. Number 6, they're asking you for highest pH. When we talk about pHs, well, what do we know? The lower the pH, the stronger the acid. So the strongest acid is going to have the lowest pH. And then as you go this way, you would have a weak acid. Finally, you have neutral. And then it gets high when you get on the basic side of it, right? So the base side. So if we look here, HF is a weak acid. HCl is a strong acid. HBr is a strong acid. HI is a strong acid. And HClO4 those are all strong acids. So this, that, and that are strong acids. Therefore, HF would only break apart a little bit. So its pH, since it's a weak acid, would be higher. And that's what it's asking you. Number 7 says rank the following of these in order of increasing acid strength. If it's a polyprotic acid, it means it has many protons. So for example, if this is H3PO4, what we say is this happens in many steps. It happens in 3 steps because each H comes off one at a time. It gives an H there, it's an acid. you get H3O plus plus H2PO4 minus 1. Whoops, minus 1. And then you take H2PO4 minus 1, and you're going to add it with water, and then what's going to happen, again, it's going to give an H because that's what acids do. You're going to create H3O plus HPO4 2 minus. The last thing is HPO4 2 minus will react with water, transferring an H. You'll get H3O plus PO4 3 minus. What we say is each H comes off less and less. So this Ka value would be the largest, the second Ka value would be smaller, and the third Ka value would be even the smallest. So when you go to rank polyprotic acids, the correct answer for number 7 is going to be C, because the one that comes off first is the strongest, second one is the little less strength, and the final one, or the weakest one, is going to be the last H coming off. 8. It says the solution has a hydroxide ion concentration of that. What is its hydronium ion concentration? Well, pH land H3O plus times OH minus is equal to 1.0 times 10 to the negative 14th. So if I go to solve this, what do I have to do mathematically? My hydroxide concentration goes there. So all I would do is take 1.0 times 10 to the negative 14th divided by 7.74 times 10 to the negative 5th. And the correct answer for number 8 is going to be B in that case. Next. Number 9. What is a hydronium ion concentration of 0.0053 KOH? Same thing. I'm starting with OH minus. I know that H3O plus times OH minus is going to get equal to 1.0 times 10 to the negative 14th. So all I have to do, if that's my OH concentration, I take 0.0053, the constant divided by 0.0053, and ultimately I get B. Next one. What is the hydronium ion concentration of 0.0016 BaOH2? Remember, there are 3 strong acids, Ca parentheses OH2, Ba parentheses OH2, and Sr parentheses OH2. Be careful, you have to double times 2 the amount of OHs. So if I look right here, notice I have 2 OHs right there. So what's the first thing I do? I take that and I double it to 0.0032. Why? Because when this breaks apart in water, you get double the amount of OHs. So when you go to do pH land on this thing, you have to go H plus times OH minus is equal to 1.0 times 10 to the negative 14th. And I'm going to take 0.0032 because I'm going to double it, and I drop it underneath there. And that's going to give me my correct answer. Be aware of that when you look. If it has double OHs, you have to double the molarity. Number 11. This is a strong acid. In fact, I could ditch the heartbreaker now that you know that. I have H+. So all I have to do is take the negative log of that to find pH. So in number 11, the negative log of 0.064 is going to be 1.19. Okay? 2 digits on the pH because it has 2 significant figures. When you take the log of it, it's decimal places. If I look here, a heartbreaker right there, H+ means it's a strong acid. They're asking me for POH. Well, if I take the negative log of it, I take 0.026, get the negative log of that, I get pH, and then pH and POH, the relationship is equal to 14. So in that case, your correct answer, when you subtract the pH from 14, you're going to get D, 12.41. 13, equilibrium expression, aqueous solution of nitrous acid is a weak acid. So we know acids lose H's. So I write it with water, transfer an H over. What do I get? H3O plus NO2 minus. When I go to put in the equilibrium expression, I'm going to put this and this products over reactants. I ignore water. So I'm going to get H3O plus times NO2 minus, and that's going to give me A. A would be the correct answer for that. Next one, 14. When it talks about a strong acid, when you have weak acids, how do you rank them? You rank them by their K value. The larger the K, the more products there are. So I look at the numbers. Well, if I look, negative fourth is a lot larger than negative fifth, so I automatically eliminate those. Then I look which one of these has the largest number. 10 to the negative fourth with 3.5 means that that would be the correct answer. So 14. that would be the strongest acid because it has the strongest Ka value. 15. What is a hydronium ion concentration of 0.35 HCN? Notice I have a Ka. So since I'm solving for a weak acid, I say x squared over molarity is equal to my Ka value. If my Ka value is 4.9 times 10 to the negative 10th, I put that in for Ka. I drop my molarity down there at 0.35. X squared, whenever this is Ka, remember x squared is the exact same thing as H plus or H3O plus. So I basically take 0.35, take the times 4.9 times 10 to the negative 10th. There's my setup. I'm solving for x. When I solve for x, the correct answer is C. Last problem. I'm asking for pH now. Notice I have a Ka value. I have a molarity, so it's going to be x squared over molarity is equal to Ka. So then I plug in my Ka value, which is going to be 6.3 times 10 to the negative 5th equals x squared over molarity, which is 0.025. Set it up like that. When I solve for x, remember x is going to be equal to H3O plus concentration, so I have to go to pH land. The way I convert it is take the negative log of that. So ultimately, when I do that, solve for x is going to give me H3O plus. I take the negative log of it, and then I realize my pH is 2.90. One key thing to remember is if you're solving a weak acid problem, x squared over molarity is equal to Ka. That's a weak acid. If you're solving for a weak base, and in this case, x is going to be equal to H plus, x squared over molarity is equal to Kb. In this case, if it's a weak base problem, x is equal to OH minus, so you have to take the negative log and then subtract it from 14. This should help. Review this and then review that worksheet we did in class, and you'll be all set to go.